Right, I'd like to start. Thank you. So my name is Suzanne Anderson, and I will be presenting the high voltage lifter. So in the problem description, it says to construct the most powerful lifter possible with a surface area below 0.1 square meters. We interpret powerful to mean that it can lift the most amount of weight, including its own weight, so it has to be able to fly. And you can see a little bit of pictures of all the lifters we built. I do not know what just happened. Yeah, okay, so a little bit about the anatomy of a lifter. We have this framework that has to be electrically isolating. We have this aluminum foil, and we have a very thin wire up here. The important parameters of the lifter is the air gap between the wire and the aluminum foil and the width of the aluminum foil, the length of the wire, and just the type of the lifter in general. So a little bit about the theory. When we apply a huge voltage difference across the cathode and the anode, where the cathode is the wire, we have this electric field that's uneven. It's very dense around the very thin cathode. That's this important part. When we have no voltage applied, it's also important to know that in the free air, there is positive ions, there's electrons and neutral molecules. So when we apply a high voltage, all the electrons, if we apply positive voltage across the thin wire, they're accelerated upwards and they hit these neutral air molecules and actually ionize them. What's also happening is that the ions are being repelled downwards, and they also hit the neutral air molecules when they transfer their momentum to them. So you have this downwards thrust, which lifts the lifter. A little bit about the theory. We have a corona inception voltage, which is the voltage at which ionization starts occurring. We use Peake's law for calculating it, but for Peake, he had two wires of equal radius. His law states that we need to use electric field strength, which is around 30 kilovolts per centimeter. We have this air density factor that's around 1. We have a Peake's value, which is given here, and we have an irregularity factor of the wires. For smooth wires, it's around 1, so that's what we used. We also have the radius of the wires and the distance. Now, because our system is asymmetric, we can only calculate a range for this corona inception voltage. So to go to the theory of the current voltage characteristic, we start with a Poisson equation, where we split this charge density into the ionic space charge and the space charge density of the dispersive phase, which is given by this. It has to do with the polarization of the ions. We rewrite this in cylindrical coordinates because it was originally made for duct precipitators. And the solution to this is given here, where this term is the electric field intensity at the surface of the coordinating wire. Now, a guy named Cooperman, well, Townsend's actually the guy who made this theory, and a guy named Cooperman slightly fits it to fit a wire plate capacitor setup, but where this is the anode plate. So he got this very big equation. I can go through the theory later if you have questions. But since our anode is not a plate, I changed this to estimate it to the top half of like a circle, and I insert that into his equation. So this is for the current and voltage characteristic. Now we actually want to calculate the force. So we know that charge is given by current times distance over this drift velocity, it's this term, and we know that the drift velocity is given by the ion mobility times the electric field. Now we can input this in an equation for force, and we end up with that force is equal to current times distance over the ion mobility. And if we input, instead of the current, if we input this very big term, we end up with our final equation, which is here. So this is the theory that we're going to be using. Now, since I could only calculate a range for my corona inception voltage, that is a fitted parameter that I'll show you how I estimate. All right, so the optimization factors is the wire diameter, the air gap, the aluminum foil width, the size of the lifter, and the type of lifters. Yes. For our experimental setup, we have the lifter here, and we turn it upside down so it presses down on this foam plate that's isolated, and we measure the force, or we measure the weight with which it presses down, and from there we can calculate the force. We have also tried with another setup where it's standing upright on this plate, that is not on top of the weight. So we have this string that you cannot see that's connected here down the hole and on the weight, so it measures the thrust upwards, so it measures the negative weight. We also have a third setup that I unfortunately don't have a picture of, where it's on top of a very long tube. But we use the first setup because it's just easier, and there's no real measurable difference between the three setups. Alright, so for the first optimization, wire size, we tried with two different wire diameters, and we expect the thinner one to work better because this field here will be a lot denser, so it will be more capable, the corona inception voltage will be lower. And for our experiments, we have the force that we measured in millinewtons, and we have the voltage in kilovolts. Now our voltage supply only goes up to, at a maximum, 19 kilovolts, which is not a lot. But we see here that the corona inception voltage, which is the point at which we start measuring a weight difference, is lower for the thinner wire, just as we expected. So for my theory, I fit this parameter. I look at the graph, I see, okay, the corona inception voltage is at 10.2. I input that into the equation. If I put, instead of 10.2, if I put, say, 17, it would be the same graph, it would just be moved and go here. So yeah, that's my own fitted parameter. For the optimization of the air gap, we know that the corona inception voltage is proportional to it in this fashion, and we know that the force is proportional to it in this way. So the smaller the air gap is, the smaller the corona inception voltage will be, and the greater the generated lift. But you cannot make it too close because the breakdown of dry air will occur. You might remember that before I said it was at 30,000 volts per centimeter, so you might think, well, our setup doesn't even get close to reaching that. But unfortunately, our field is actually uneven. As I said before, we have a dense field here, but on the anode, we also see that the aluminum foil is a little bit crinkled. It was very hard to get it smooth. And we see that at the corners, it kind of cuts off and has these sharp edges. So the field here is also very intense, you could say. And I have a video where you see this. It's actually called electrical arcing, but I'll just call it sparking because it's easier to pronounce. So, for the air gap, we tried different distances. We see that, yes, for 2 centimeters, the closer it is, the better, but our graphs cut off here. That's because it started doing the sparking. So for our setup, 2.5 centimeters is actually optimal with the voltage supply we have. If you have a greater voltage supply, this is taken from this guy who had a voltage supply that went crazy far up. You see that the air gap can go up to 21 centimeters. So the greater your voltage supply, the bigger you have to make your air gap to avoid the sparking. Alright, aluminum foil width. That is something that my theory does not take into account. But you know that when this downwards drift of neutral molecules and ions hit the anode on the bottom, they have this drag force here. And we know that if we just have a cylinder, the drag coefficient is much higher than if you have this elongated, you can say, wing-type shape. So the longer it is, the better it is. We see that the experiments start at the same corona inception voltage, approximately, but they differ when they go up here. But I didn't understand why 2.2 was actually worse than 1.8. I would expect 2.2 centimeters to be better for the width. So I went into the wind tunnel and I measured the drag coefficient, and due to some building mistakes, it could be that the aluminum foil was crooked. We see that 1.8 had a lower drag coefficient, so it makes sense that it would be less drag. Yes. Alright, size of the lifter, bigger the better. We see that it depends linearly on it. So the bigger you can build it, the more force you'll generate. But when you also reach a certain limit, you need to add extra support pillars that weigh down your lifter. I mean, these lifters are 1.5 grams, so it's not a lot of extra weight you need to add. We see here, not surprisingly, that for a lifter of 20 centimeters, it's twice as good as one that's 10 centimeters. So that's a linear dependence there. Alright, types of lifters. We tried building this hexagonal lifter, which ideally should work better because we have going from a triangle to a hexagon type, we have a length that is 4 times greater, but we have a mass that should be less than 4 times greater. But this hexagonal lifter was really difficult to build. There's just, I mean, if a machine could do it, it would definitely work better, but just, you have human errors when you're building these things. So we see here that you've noticed so far my measurements have actually been a little bit above my theory, but for the hexagonal lifter, it's a little bit under, and that's due to these building mistakes. But it is approximately a little less than 4 times better, which was what I expected. All right, so in conclusion, we see that the thinnest possible coordinating wire is better because the electric field is more dense around this cathode. We know that the air gap depends on the voltage input. I mean, if you have a huge voltage supply, you have to make the air gap greater. You want as much length as possible without the extra support pillars, so the hexagonal type lifter should work better, but yeah, due to building mistakes, it didn't. Also, you want long, straight aluminum foil width, but again, there's a little bit of a trade-off, because the drag, it's not a huge drag force that you experience, so the longer you make the aluminum foil, you're just adding more weight to it. But for us, we saw that 1.8 centimeters worked. Also, hexagonal types are more efficient than triangulars, or they should be, but again, it depends on how you build it. So in conclusion, we know that the force is proportional to these factors in this manner, where there's a trade-off between how much weight you're adding and whether or not electrical arcing or sparking will occur. But the very ideal lifter would actually be a circular one if it was possible to build, because it wouldn't have any of these sharp corners that can cause this electrical arcing. But again, that's very hard to build. All right, and thank you for your attention and time.
Very much for the presentation. Now it's time for the questions from the opponent.
Can you please show me the second slide? The next one, sorry, and the next one, the next one, and the next one. Okay, so for which polarity of coronavirus this theory is applicable?
I'm sorry, what?
Which polarity of coronavirus is considered here?
What, molecules?
Polarity.
Polarity.
Is plus or minus?
Oh, I applied positive here and negative here. But you
What
can
will
also
change?
flip it.
What will change if we change polarity of coronavirus?
It's a question for the discussion.
Okay. The next question: can you please show the plot on which you take this plot from somewhere? Voltage depending on difference between electrons, something like that. Force depending on different distance between electrons.
Between distance. Here.
No, the next one. This
one.
How can you comment that at high voltages your theory is wrong?
You mean why it goes flat? It's because there's no, you reach a limit where it's ionizing the air molecules faster than air can come flow into your system, so you get this, it evens out eventually. If you could have like a continuous flow of new air, then that would change this.
You tell that the optimal gap is a breakdown gap, but then you tell that for high voltages it's not so. Do I understand correctly?
Eventually it evens out, and even if you apply higher voltages, there isn't any more air to ionize.
All right, thank you. Could you please show me the picture or the video of the most powerful lifter you have constructed?
I don't have that video here.
Or could you describe what it looked like and how?
Yes, it was actually triangular. It was 20 centimeters on each side, so a total of 60 centimeters. It had a distance of 1.5, and it had the thinnest coordinating line.
Was the wood the
Time's up. Now it's time for preparation of the opponent's speech.
Can I start?
Yes.
Good morning, ladies and gentlemen. My name is Platon Dmitriev. My name is Platon Dmitriev, and I'm representative of the team of Ukraine. And right now I'm going to present my opposing speech to the problem number 11, called the lifter. And first, there's our team. Thank you for all the job we have seen. There were a lot of it. we have seen as theoretical equation some theoretical model. Then you try to compare it with using some plots with your experiments. And finally, we saw this lifter that even tried to fly up. So that's why I'm going to analyze your report step by step. And here I have both advantages and disadvantages. Let's start from the model. So you define the most powerful lifter as a device that can lift its own weight, like some mass, including its own weight. We do not completely understand it because the lifter which cannot lift its own weight is not a lifter. So probably, well, we have an imagination that it did it just because it was not flying all the time. And probably that means that the lifters you make are not the most powerful. I want to address the formulation of the problem one more time. It has to construct the most powerful lifter. And that is why in my opposing speech I will try to look at the problem from both sides, physical one and the technical one. So how should I, as a person who does not know the theory, compare of the details of the lifter in order to make it fly and to be the most powerful ever? So then he tried to explain the effect, and it was explained rather good, but nevertheless we have some questions. For example, you have this illustration with a little wire in the diameter and the aluminium foil, but all the field lines are going from one circle to another, and we have a question: what do you need the other part of the foil for? So we do not say that it is not necessary to have it, but we just want you to explain this moment and probably try to tell us how to optimize the length of the foil. Well then, you explain the theory of corona discharge appearing. You rush through this theory rather quickly, but nevertheless we tried to get all the points. We suppose that he did not take into consideration humidity, and while you tell us about this problem, you told that this theory is applicable to the electrodes with the same radius. We want you to specify this question one more time. So the general question which I want to underline from this part is the limits of your theory, when it can be applied and when not. Then you told us that the bigger the better. But I suppose in the formulations of problem we have 0.1 square meter, and it was given just for optimizing your setup. So with this data you can compare lifters of the same surface but different shapes, and probably calculate something, probably calculate the mass the lifter will have after constructing. And yeah, I have some more points touching this experiment. So first is where is the flying lifter, but well, in the end of the presentation we can see. But we are still not sure that it is the most powerful, as problem said. Then in the conclusions he said that circle lifter is the best, but again, how to construct the circle lifter is not very clear, and how it can be the conclusion. Well, we want you just to comment this from the technical side of the problem. Well, I have not much time left. I suppose we'll discuss all these questions in the polemics. But one more thing I want to say, that again, from the technical side, we've got this balsa wood that has real large currency losses, and probably you could try to exchange it for something else. Probably you could take a tubes of less weight or something like that. But anyway, the report we saw was rather great, and you get really good results. And now we're trying, I guess, to compare it in a good structure and maybe make it even better. Thank you.
Thank you. Where would you get
Let's move to the discussion.
Hi, just to start with the balsa wood, so the last thing you mentioned. Actually, when you see that electrical sparking, when it occurs, it changes the resistance in the wood, and you have to build a new lifter. That's why I built I think around 30 lifters. And I also tried using like the drinking straws, the very thin cocktail ones. That also worked, but I think the balsa wood was just easier to work with. So I didn't try different materials. I don't know yeah, you mentioned humidity. Let's take that one. The humidity does have an effect. I tried doing it on a wet day where I left the window open and there's air, it was raining. And I tried it on a dry, sunny day, also with the window open, and I saw about a 4% difference, so it's not a huge factor, but I did not take that into consideration, but from that point on, when I did all my measurements, I tried doing it on dry days, and I had the window closed, so it was a more closed environment. I don't know if you want to talk about the foil.
Yeah.
Yeah, I can draw that up.
Please switch to your presentation.
Oh, yes. It's actually up there. You can use other things than foil. I mean, you could just use a thicker wire also. It just has to be something that's conductive.
Go back to the slide with on the spreadsheet.
Where I have my measurements.
Somewhere in there.
I mean, this is the only part I talked about the foil.
You have this explanation with the wires, thin one and a thick one.
Oh yes, that one, yes. There we go. Yes. I mean, yes, here you see that the foil is round, but in actuality we have this long elongated foil. It's mainly just the field here that's important, because the field that goes out here does not have a huge effect. And the corona and such, I mean, the ionization actually only happens in this field. You just have to make sure that it's not dense enough here to ionize air also.
So that sometimes means that we can cut just those foil away in order to last the mass of a liter.
But then drag goes up. Because I showed that thing with the drag, that if you have a foil that is like this versus a foil like this, the drag force on this is a lot lower than this. So that's why my measurements were better for the foil that looked like this compared to a smaller one, or even just a round one. I tried to get a round one too, but it was really bad. It didn't actually fly, so it's not in
I
my...
just wonder about the losses. So which losses would be bigger when you use the slump foil and have a lot of mass, or when you use a drag force that just doesn't let you go? But actually, drag force doesn't exist when it tries to lift up at once.
Yes, it does, because you have this air that's coming down here like this. You have, I mean, the ions are hitting neutral air molecules and accelerating them downwards. So if you have a shape like this, there's a lot more drag on this compared to this shape. So drag does have an effect.
Right. So can I ask one more thing? Can you go back to the 10th slide? Like, you read through it rather quickly, but my team tried to make a photo of this final formula, and they say that the dimensions are not correct.
The final formula is this one.
Oh, this one? Which one? Previous. This two? So we say that the dimensions are not correct. Like, I'm not insisting on this right now, but if your team can check it, please. So we have some misunderstanding. Thanks.
Yes.
I had some questions about this technical issues about implementing a fair model of lifter and the surface.
Yes, I understand that your team understood the maximum surface area as when you look at it from above. We understood it as the surface area of all the materials. My hexagonal lifter is exactly 0.1 square meters when you look at the surface area to the aluminum foil and the sticks. So that's...
If I have time, can I explain what I'm talking about? So, if you have some like upper limit of the surface,
yes,
whatever it can be, you can have like you can have a limit of weight, so you cannot use more materials that it can require. So that is why your lifter can have some limited mass, lifter of each form of each construction, and that is why you can compare its mass to its possible
Okay, please finish the question. And now it's time for the questions from the reviewer.
Hello everyone, I have a question for the reporter.
Yes.
In your theory, after that you use the Higgs law, do you assume that the field between the electrode is uniform?
It's not uniform. I mean, I actually have a slide for that. It's in my appendix. Yes, here. I calculate this range for using Peake's law, and Peake's law does take into account how the field looks. He uses, if you have a wire here and a wire here, he uses a wire radius.
Okay, but not just between the two electrodes, not in the coronal region. Is the field? Do you consider the field uniform or not?
Yes.
Yes. So that's one question. Now, a question for the opponents. You mentioned the theory, but have you understood the key concepts of the theory?
Yes.
And if so, would you be able to summarize them?
Would I be able to?
Would you be able to sum up the theory and what are the main points of the theory?
Okay. So as I saw, there are some maybe misunderstanding or some mistake in the theory, but nevertheless it can be like a simple mistake or something like that. Generally, I suppose that we agree with those theses which are explained there, maybe with some minor changes.
Okay. That will go for me.
Okay, thank you. Now it's time for preparation of the reviewer.
I think I'm ready.
Okay, now 10 minutes to the reviewer speech.
So, to begin, thanks both the reporter and the opponent for their discussion so far. I would like to begin my review representation with the strengths of the reporter. To sum up the presentation, the reporter clearly defined what is powerful, and instead they list the important parameters that they studied the effects. The main point of the theory was the Higgs law to estimate what is going on the coronal region, and then the assumption of uniform field to calculate the different quantities in the other region between the electrodes. I would like to emphasize that it's a huge amount of work done because building a lifter is very hard and you have to be very cautious. So building 25 meter or I don't know is a huge amount of work. And experimental optimization was good and some effort to compare it to theoretical predictions, and the list of parameter studies is quite impressive. In overall, it's a brilliant presentation with strong experimental assets. Now going to the strength of the opponents. You raised the question about humidity, which was maybe a parameter to be taken into account. After the discussion, it proved that it wasn't the case. You mentioned the shape of the foil too, because that was not clear between if the theory was taken into account. The question also the experimental protocol, but at the point I would like to go back forward. And you questioned the theory with a strong accusation. Maybe it's true, I don't know, I haven't checked yet. And you went back on the subject, questioning the definition. What about the force? What about the maximum force? Now, showing your weaknesses, you did not question the key physical concepts that are underlying the theory. I'll go back to explain that later, but I think it was missing. There was a systematic disagreement between the theory and the experiments on several slides that you did not question about. You did not question the hypothesis of the uniform field between the electrodes. That would mean that it would be the same with two infinite plates with the uniform density. And why is there a difference between two infinite plates and the circles? Why are there three experimental setups? The experimental difficulty was not clearly underlined. And the theoretical prediction, what is the maximum force? I would like to lead the discussion to why does the lifter lifts? Because I think we didn't quite clearly understood why is it, and maybe also point of shape optimization.
I would like to very first start, because you guys said my theory did not check out. I have checked units on it, it does check out, but I got worried that I might have written the wrong thing. I did not. My team checked it and it is correct, so yes. Going back to why does the lifter lift, because that's actually a really good question. I know I go through it very quickly. If I can draw it on this board. You have the thin wire here, and you have your aluminum foil here. What's happening is when we apply a positive voltage, these ions are moving down, and they're hitting, if there was no neutral molecules, they would generate a lift here, but then they would also hit here, so nothing would happen. But you have these neutral air molecules that they hit that diffuses, their momentum is diffused to these neutral air molecules that are moving out of the system. That is why this force is a lot smaller and you generate actual lift. So that is how that works. And also a good question about the polarity that you brought up that we never got around to discussing. If you switch and you have negative here and positive here, you will have ions moving upwards towards it, and that will generate a negative force here. And you hit these neutral molecules that also diffuse out of the system, so it would be less effective.
Thanks for the comment. That's I guess exactly correct presentation. And yeah, probably I can answer some points that if you had to make, besides that I didn't like the physical concepts. Actually, we, as I told you, we mostly agree with the reporter about all the theoretical concepts, and that's why we're trying to talk on some other topics that can be also raised in this problem of optimization and construction.
Okay, my main critique was maybe there was some lack of pedagogy in order to make the jury and the public understand what are the physical concepts. I know we know them, but maybe other people.
So, can we continue?
Yes.
I've got some points. So, about the dimensions, we still insist that that last formula on the 10th slide. Well, please double check. Okay, now it's alive. Yeah, can I please launch your presentation? Yes.
Sorry.
So, you had this plot on which you checked the force depending on the voltage that you apply from your source to the lifter. And yes, this one. And so you have this very little error bars from you for kilovoltage measurement. And what I'm going to ask you about is, are you sure that the voltage that you try to get to your lifter from your source is the same as it appears on these two electrodes?
It is not, but it is on this graph, sorry to clarify, because I have a voltage input and I measured across the graph using a voltmeter. I mean, my voltage input was actually 24 kilovolts, but the lifter only experiences 17.
It's okay. Where did you connect the voltmeter?
Oh God, I don't remember. It was in parallel, I'm pretty sure. It could be, yeah, no, it was in parallel. But,
Okay.
yeah. Yeah, I did these in November, so I'm a little...
I have one point to raise. To answer to the subject, you may have stated that the reporter does not give, doesn't emphasize what is the maximum output force that she obtained with the lifter. Considering in graphs, it appears to be around 40-50 millinewtons. But the main point, unless you could have questions about what is the theoretical prediction of the upward force and how the lifter, the experimental upward force is efficient compared to this theoretical prediction of the upward force.
Now, I would like to say that now is the time for general discussion. All of the members can take part. Yes,
So I want to raise again this question about the surface and the construction. Yeah, in the previous telemetry we didn't finish with a question about the surface and the limited mass you can calculate. Like, if you have the limit of surface, you can calculate the mass. The limit of mass, your lifter will be not bigger than.
I mean, the mass depends on how you build your lifter. You have support pillars. That's why the hexagonal would be better because it has less of these support pillars. I also have that in my appendix. One moment. A little bit crude drawing from above. We see that for a triangular one, you have these three beams where the ionization is actually happening, and you have these support pillars. Hexagonal one is 4 times the length, but only 7 support pillars. So there's an optimization of mass in that. But again, it's just more difficult to build. I had a lot of difficulty
You
with
don't
Hexagonal.
have the same surface. What would be the
No, I have the same surface. It's 4 times greater, but you don't have the extra sticks to support it. I don't know if that's the answer.
I'd just like to clarify the point about the units. I mean, what our theory states is that it has units of epsilon 0 times a voltage squared. I don't know, maybe it's because you see the CIV and you think that it's C times I times V, but that's the corona inception voltage. I mean, epsilon 0, that's farad per meter, and that's...
Maybe the discussion about units is not very important, maybe you're right, but I'd like to go back on this point of optimization. I know it's very hard to build a complex lifter with many pillars in the middle, but let's assume that you could. What would be the substructure pattern which should you use to maximize the upward force? Because the more substructure you have in it, the more force is generated because you have more length of electrodes. But if you completely fill your lifter with pillars, and the force won't be there, so there must exist a maximum concerning the substructure pattern. So what do you think, or maybe the opponent thinks, that is this maximum? If you would assume you could build a lifter the way you want.
I did mention that I think the optimal lifter is a circular lifter if you can build it. Because you can just build it bigger and bigger until you reach that limit, the 0.1 square meters, and it wouldn't have those kinks in it that causes electrical arcing.
Okay, that's what
I want to agree with reporter on this point. So we have to maximize this perimeter, but you also have to take into consideration that you need all those pillars in order to make it stable and just to stay alive while you're going up and down. And that is why you also have to take into consideration its mass and technical moments.
So, I have a question. Your theory proposes to increase voltage as maximum as possible, yes?
Yes.
But what about technical realization of this more point? Wouldn't you advise, for example, more melt or something like that?
Would my what?
Well, melt or fire or something like that.
Oh, well that's...
And what about losses in this case?
Yes.
This little foil components.
Yes, that's why you would have to change the distance between it. I tried with some very, very thin Kanzel wire that was 0.05 millimeters in radius, and it just broke because it was too thin. So there is an optimization there.
And just on top of that, what gives you the guarantee that what you had predicted theoretically as an optimal lifter is actually implementable in the reality, considering all the corona losses that are possible in the corners, all the melting that happen due to high voltage, etc.?
That is actually the biggest uncertainty that I have not included in my uncertainty calculation, is from when you're building it. You have these building mistakes, and especially the aluminum foil, that it's not smooth. So that is a huge uncertainty that I have not accounted for.
Have you faced this uncertainty when carrying out experiments?
I'm sorry, what?
Have you faced this uncertainty problems when carrying out experiments?
Yes and no. I mean, my theory and my experiments are fairly close together. They do disagree a little bit. So, yeah, I mean, I have seen it, but it's not a huge impact.
Thank you.
So now it's time for the discussion is over. Concluding remarks by reporter.
Right, well, I've been working on this for half a year. As you said, lifters are hard to build. Yes, they are. But it was a very fun question, and I would like to thank whoever proposed it for this tournament, because I had fun building these things. And just thank you for the opportunity to be here.
Now it's time for questions from the jury.
Thank you for a very nice effort on three of you. It was very interesting. On one point, when I grade exams, it doesn't really matter how well a student has solved the problem if it so happens that the dimensions are incorrect at the end. Then I give 0 points, even if it's a technical question. Now we had the instance where the opposing team comes with a serious accusation of dimensional mistakes. And the reporting team says it's correct. So I would like the opponent to just show, do a quick calculation and explain why he thinks the dimensions are incorrect.
May I show it? Actually, I don't remember exactly, but I will write just dimensions of passages which have dimensions. Okay, it's kind of this stuff. Epsilon 0 is a down, okay. It's farad per meter and okay, farad per meters and length is meters and also what the square we have. Meters in square. The denominator and what is it? And I forget this. Oh, mobility. It's a.
No, mobility isn't.
What?
The mobility is not in it. It's cancelled out.
We said about the previous slide.
Yeah, that was for the current
Yeah, look at
voltage
the
characteristics.
formula. So you go back to
Yeah, this one, both of them. It doesn't matter. And mobility here is a velocity per field. So I do the mistake. And so what I should do next? I just multiplied it. And then see the form, I found extra column in the denominator. That's it.
So what you get? So this is the formula for slide 10, and this should become current. Is that right?
Yeah, I found
And what you get it?
extra column. Actually, the column is here. The column is column is here, column is here, and column is here. They are all cancelled. No, here column in the numerator. Here column in the denominator twice, and here column is denominator.
Okay, so
Okay.
I just want to continue this question and ask the reporter, what mobility did you use in this formula?
I use ion mobility for positive ion.
Which is its different definition?
What do you mean?
It's the ratio of the velocity to force, or it's other thing?
I'm not sure I understand the question.
There are two definitions of mobility in different parts of physics. There are two definitions of mobility in different parts of physics. In one of them, we do have a velocity per unit of force, and in other it has the velocity per unit of charge.
Yes.
And force. So the charge could be included in the mobility or excluded.
The thing
That's
is,
the problem.
the mobility cancels out in my term, so I don't actually have it. I mean, here it's not a part of my final equation because it cancels out.
Yeah, I see.
Like I
Because
use
it,
the positive ion mobility.
Okay, we got the definition of mobility. Yeah.
I just wanted to make sure that I understood well how you understood the surface area. Could you just make explicit drawing, for example, what is a surface area? And second, make an explicit statement how you define your figure of merit. What is your best lifter or most powerful?
The surface area, say I have these 3 support pillars, and I have the aluminum foil between them and the thin wire. The surface area is this aluminum foil on both sides. So I have aluminum foil here, here, and here. I take the surface area of these support pillars, and I added the wire surface area, the very thin one, but it was very negligible in comparison. And as on my concluding slide, I said that the best lifter is 60 centimeters. You have a length
where each of these is 20 centimeters. The distance for my voltage was 2.5 centimeters in the thin wire that I used. And
My question is, if you have two lifters and you compare them, which one wins? Which one is better?
it depends on what parameters you input. If this length is longer, then it's the longer one that's better. If you have that this is closer without electrical arcing, then that is better. If you have something where the mass is less, then that is better. And also it depends on the width of this compared to how much drag is there.
But I still don't get the point. Is it the lift force per unit area or is it lift force per unit mass? You have to define a figure of merit here. What is the most powerful? What exactly does that mean?
It comes from how much mass your lifter has. So that's per mass. Yes, that's how I did it.
Okay, I'm sorry, I have one or two more questions, small questions. Could you please switch to the end of the presentation where you have force formula?
Force?
No, next slides. You have some formulas there for the force.
Here, yes.
Next.
It's just to say how it.
Yes, could you switch to the next slides? Yeah. You had there some dependency where was the dependency on the R and other factors. Okay, I don't see this formula now. Now let's switch to other question. You had some plots that didn't begin with the voltage, which begin from the voltage 0. How would you explain that there is no threshold for the voltage?
I mean, I start from 0 volts and I turn it up until I start seeing the lift. This is the corona inception voltage, this point at 0. That is where the ions start becoming ionized. That is why my plots start from these points.
Okay, time for questions is over. Now it's time for grading of the jury. The grades for the reviewer, Team of France. 9, 8, once. 9, 8, 9, 8, 8, 8, 8, 8, 8, 8, 8, 9, 9, 10, 9, 8, 7, 8, 8, 8, 8, 9. For the opponent, 8, 8, 8, 8, 7, 9, 7, 7, 7, 8, 7, 7, 9, 8, 7, 8, 6, 7, 8, 9, 8, 7, 8. And for the reporter from Denmark, 7, 7, 7, 8, 8, 7, 8, 8, 9, 9, 9, 9. Seven, 7, 8, 8, 7, 8, 8, 9, 9, 9, 9, 9, 8, 8, 7, 6, 9, 8, 9, 9, 10, 9. So now it's time, I think, for jury remarks. Maybe Vladimir. Okay, this time I have two remarks, one for the opponent and one for the reporter. Firstly, I want to comment about the opponent team. You spent a lot of time making this very serious accusation about the dimensities, but that was a problem that you even didn't ask about the mobility. In which terms is it written, and there are different definitions of this term. And what was our problem? The second problem was that, as I think, you focused on some of the important points. For example, some of your points were very good. Point for the if the surface was the same, for example, triangle and hexagonal shape, as we have seen from reporters from the report, if the length is 4 times higher, then the surface will be somehow bigger. But you didn't focus on a lot of points that I didn't mention that I mentioned for myself, and reviewer did a good job when he raised some more questions. Okay, about the reported team of Denmark, I'm sorry for this really low mark, but I think that there were some serious problems in both of your theory and maybe experiments. Firstly, I don't believe that there could be 4% difference when you change the humidity for a big value, because all the formulas that you have shown, they include the voltage of dry air breakup of electrical break, and this voltage will decrease vastly when you increase the humidity. The second problem is that, for example, we are consider that aerodynamics on your shape. If you have the same aerodynamics that is shown on the picture, then there will be corona in the bottom point of the foil. You cannot consider the foil such a shape, but you have spent a lot of time talking about this shape. And I have some more questions about your formulas. You didn't show the formulas which you wanted, but there surely was formula where was a term 1 divided by square of r plus 1, which has problems with dimensions. And I think that some of your ports had not clear threshold for the some corona inception voltage, and that was the problem that I didn't like about your port. Maybe there were some problems of measurement. Okay, thank you.
I'd like to comment to the reporter. Actually, as I see, you didn't answer the question of the problem, because you just made a theory which was questioned and somehow proved it experimentally, but you didn't construct the most powerful lift, and nor you didn't recommend how to do it. Or maybe I didn't understand how to do it from your report. And thanks to the reviewer, he mentioned this problem of your report.
So my comment is in line with the previous one. What you presented was, let's say, 90% theory and 10% construction. When the problem starts construct the lifter, I think it should be quite the opposite. You did not optimize materials, for example. You could use mylar foil instead of metal foil, and then it conducts as well, and it's 10 times lighter, then your weight would decrease dramatically. So there was very little construction effort really presented here. Thank you.
Any other remarks? Okay, I don't see. So now we have 15 minutes of coffee break.